Hi everyone, we're going to start working on changing the appearance of rational expressions. There's a few different ways to do that. We're going to start with reducing them, and this is exactly why we went through this exact same thing with constants earlier, because it's the same trick. So if you understand reducing fractions, you understand reducing rational expressions. It might look worse, but we're always looking for the simple problem hidden in the messy problem. Variables just represent numbers, so when we throw variables in the mix, we're still doing the same thing as if they were numbers, right? So I'm going to start with just plain old reducing fractions. Remember, the idea is we're looking for factors that the top and bottom share. So the top and the bottom in this case share a factor of 4, which means we can use the fact that 4 divided by 4 is 1 and cancel it out, right? If I'm multiplying by 4 and I'm dividing by 4, those are inverse operations, so they should cancel, and I just get 5/3. And this is exactly what we're going to try and do. Sorry if that made your eyes go wonky. For rational expressions. So we're going to start simple and work our way up. This very first example, 6w divided by 15w, it's the same idea. We're looking for factors that they share. You can do this all at once or in stages. Right off the bat, I see that I'm multiplying by w in the top and bottom. So if you multiply by w and then divide by w, those are inverse operations. The w's will cancel, so I'm going to get rid of them right away. And then the 6 and the 15 share a factor of 3, so if I cancel a 3 out, 6 is 2 times 3 and 15 is 5 times 3, we're just going to get 2/5. So exact same thinking as above, it's just that one of our factors is represented by a variable, by a letter, okay? So regardless what the value of w is, one exception, w can't be 0, or this is all garbage. Otherwise, regardless of what the value of w is, it should cancel out. And this is actually a really good thing to point out moving forward. It's true that 16w over 15w equals 2/5, but really to make that statement through, we'd have to specify that w can't be 0, because if one side works when w is 0 and the other side doesn't, then it's not a true statement. I do not need you to write that every time, but start thinking about it. It's something that we'll need to think about with functions. Okay, number 2, it's really tempting to say, oh, well, b divided by b is 1, but notice if you walk through order of operations, the first thing we would do if we plugged in a number for b is we would simplify the top and the bottom. So we'd have to do this multiply right here, and then we'd have to do both subtractions, and then we would finally do the division, right? So subtraction and division happen back to back in order of operations, and they are not inverse operations. Because subtraction happens between the multiplication and the division, we can't cancel. So the only way we're going to get to cancel here, my dog is helping again, I'm just going to let him have whatever he's chewing, is if we actually rewrite this so that multiplication and division happen back to back in order of operations. And the way that you would change order here is by factoring. On the bottom, if you factor out the 3, now all of a sudden the order of operations is first you do the subtraction on the top and bottom. So first we subtract, then you multiply by 3, then you divide, right? Here, times, we'll do it that way. So now multiplication and division are happening in consecutive order, so we can cancel the b minus 3 out. It's not the b that gets canceled or the 3 on its own. It's an entire b minus 3. But you want to be really careful with this. What you've just said is b divided by b is 1. It doesn't go away completely. There's still a 1. There's nothing bringing the 3 out of the bottom, so this is equal to 1/3. And I think this one and the last one, this one more than the last one, it's kind of impressive sometimes, especially as they get messier, to notice that what I'm saying is that no matter what I plug in for b minus 3 over 3b minus 9 should equal 1/3. I want to point out that, again, there is an exception to this in obsession. There's an exception to this rule. If b equals 3, the first expression that we started with is undefined. It's fine for any other number, but b can't be 3. So these are equal as long as b does not equal 3. You don't have to write it for now. We will be thinking about it a lot later. Okay, so similarly for 4x over 2x minus 6, the top is already a product, right? So what we're looking at here is, again, it's like tempting to try and cancel out 2's and x's, but you can't do it because the order would be, we do the multiplication on the top and the bottom, then we would do the subtraction, then we would do the division. And if this is confusing, maybe I should point out here, fraction bars are grouping symbols, so it's kind of like they're parentheses. So people want multiplication, division to happen before addition, subtraction, but that fraction bar forces these parentheses. So we have to do the subtraction before the division. This is a quotient. So we don't have multiplication, division back to back. We need to change that. We would change it by factoring. Since the top is already a product, we're great shape there, but on the bottom, we could factor out a 2. And that's really about as good as we can do. So now we force the subtraction to come first, then we would do the multiplication top and bottom, and last, always when you write it this way, is the division. So now we're free to cancel. Multiplication and division are happening back to back. We don't get to cancel as much as last time. The only thing I can cancel out of this is a factor of 2, which means my most simplified version of this expression is 2x over x minus 3. In this case, we don't really have to worry about stating that x can't equal something because the problem x is x equals 3. And while it's true that x shouldn't equal 3, you can see it in both places. So they don't differ when x equals 3. Both of them are undefined, so we don't really have to specify that for a problem like this. Okay. Next one, 3k squared plus 30k over k plus 5. Again here, if we were going through PEMDAS, the parentheses force us to go first multiplication on the top, then the addition, subtraction, just addition in this one, and then the last step is the division. So again, we need to factor to rewrite the top and bottom as products. So the top, we can factor out a 3k, and that leaves us with a k plus, oh, what did I do? I wrote a bad problem. Okay, we're going to pretend this was a 10 from the beginning. Sorry. And then on the bottom, and we can cancel. And same thing here. Remember that what happens is not that k plus 10 is gone altogether. Really what happens is we're left with 3k over 1. The nice thing is just that writing the divided by 1 doesn't really change anything. It would change things drastically in this problem back here, a couple up. If we didn't write the 1 over, 3 is very different from 1/3, but 3k is not different from 3k over 1. It just looks a little cleaner. So it is okay when you cancel something. When nothing is left in the bottom, you don't have to write the 1. When nothing is left in the top, you need it because you can't move the stuff in the bottom up to the top. Okay, and into the messier version, you're going to get to start practicing your factoring. So we'll hit some trinomials in the mix. I don't see any greatest common factors with that leading coefficient of 1, so I'm just going to jump right into it. The good news is that with a leading coefficient of 1, your factoring is usually easier. So I'm looking for factors of 32 that add up to 12. So what is 32? 32 is 2 times 16 and 4 times 8. Okay, so I think that's what I want. 8 and 4 add up to 12. So I'm going to say I have r plus 4, r plus 8. Order doesn't matter. And then in the bottom, I need factors of negative 32 that add up to 4. And I actually think, looking at that, that I want the same pair. I want the 4 times 8. It's just that this time I get to make one positive and one negative. So let's see, if I want a positive 4r for my inside-outside, that better be a plus 8 minus 4. So I rewrite so that instead of it being addition being the last thing that happens in the top and bottom before we divide, now multiplication is the last thing that happens in the top and bottom before we divide. Multiplication and division are inverses, so we can cancel the r plus 8, and we're left with r plus 4 over r minus 4. Notice, as tempting as it is, that we should not be canceling the r and the 4 because now they're attached by addition and subtraction. And addition and subtraction are not inverses of division. They don't cancel each other out. So we're done. Here, it would matter as we get into functions that the expression we started with is not allowed to equal -8. We can't have 0 in the bottom. So the only way this is fully true is if we specify for the new fraction that r is not allowed to equal -8. So you don't have to write it now. We will be writing it later. Okay, last but not least, I wanted to give you lots of these messy things so you could see the full spectrum. Let's see, I do see common factors in this one. So I'm going to go ahead and factor out a 4 from the top. Nope, I lied to you. I'm going to factor out a 2 from the top. 2 times 2x squared minus x minus 1. And in the bottom, I'm going to factor out a 9x. So I'm going to be left with x squared minus 2x plus 1. Okay. And it's a good start. I don't have anything that I can cancel, so I'm going to try and factor the trinomials that I'm left with. So the first one, I'm going to split it up into a 2x and an x, and then I don't have a lot of choices for the last. It's 1 times 1, and the only thing I get to choose is who gets the minus sign. So if my inside-outside, outside-inside, I guess, I don't know why I always want to switch it when I do this check, are 2x and x, and I'm hoping to get a middle term of negative x. I better make that a -2 and a positive 1. So I'm going to put the negative over here, the positive in the middle. And then for the bottom, again, if in doubt at all, check. Practice your checking because you'll want to do it for tests. I'm going to split up an x and an x. And then this one is kind of nice because I don't have any choices on that. I also don't really have any choices for 1s. And since it's a positive one, they either need to be both positive or both negative. So if I have 1x and 1x, and I'm hoping to get a -2x in the middle, I better make them both negative. Okay, so I do get to cancel a little bit, x minus 1 over x minus 1. So I should have 2 times 2x plus 1 over 9x times x minus 1. And I'm not seeing anything else I can factor, and I don't have any common factors. Again, I know I have x's in the top and I have a couple of x's in the bottom. That x in the top is part of a sum, right? This plus right here hooks it onto the rest of its factor. So you can't cancel anything that gets hooked to a sum like that. The factors of the top are 2, weird things, and 2x plus 1. So you can factor a 2, you can cancel a 2, you can cancel a 2x plus 1, but you can't cancel pieces of 2x plus 1. On the bottom, you have 3 to choose from. You have a 9, an x, and an x minus 1. And you could even think about it as more than that because you could make the 9 a 3 times 3. So you could cancel a 3, you could cancel a 9, you could cancel an x, you can cancel an x minus 1. You can't cancel the x and the 1 in the parentheses separately. So anything stuck inside a factor with an addition hook to it, you can't cancel. Okay, so hopefully that helps you on reducing fractions, reducing rational expressions. Thanks for watching.